Okay, so let's talk a little bit about evolutionary solvers. So in this case, we'll try to set up an example that'll take advantage of um, an evolutionary solver. And in Grasshopper, the evolutionary solver is going to be Galapagos. And so David Redden has a pretty good explanation on the Grasshopper side of evolutionary solvers and how they work and what they're good for. But we'll try to set up an example, sort of test some of his ideas. So one of the things he mentions is, say, finding the smallest bounding box of an object, specifically an object that is not orthogonal to the xy plane. So if we make an object, let's say a box, and rotate that box in a little bit in every direction. And I'll bring this into Grasshopper. Now, if I find the bounding box of that, you'll see that it's, even though the object itself is a box, the bounding box wants to be orthogonal to the xy plane, so it doesn't make a very small bounding box in that sense. And if this is something that we want to, say, 3D print, then we might want to find its smallest bounding box so we know how to arrange that on the 3D printer to be most efficient. So how could we go through the step of finding that? Well, we might need to rotate the plane of that bounding box. Rotate plane XYZ. So this allows us to rotate a plane in 3 dimensions. And this is from our Pufferfish plugin. So let's say we can rotate it from 0 to 90 degrees. From 0 to 90. So we could try to figure this out for ourselves, rotating it around, but it's a non-trivial task. Finding the right sort of combination of these three is difficult. We could probably get something fairly close, but not exact. So that's where this evolutionary solver comes into play, where we can say, maybe try to minimize the volume of this box around this one by adjusting these things, these inputs, these criteria, or in evolutionary sense, these genes, to get the right size and orientation of this box. And so for Galapagos, what it needs is a genome, those genes that we can adjust. And so it plugs in slightly different, where it doesn't plug into the actual data that's coming through, but is just allowed to change that. And so what we need to determine if it's doing the right thing is some fitness criteria. So this determines if it's working or not working in some capacity. So this might be something that we want to minimize or maximize. If you look in double click into this, you can see the solvers and information, but you can also minimize or maximize some sort of criteria. So let's use the volume. If we make the smallest volume compared to our shape, then that should be the smallest bounding box that will work. So we can take the volume of this bounding box and the volume of our object, and we can subtract them. So this one is larger than this, we get some sort of difference in that. Now if we minimize that, it should be the closest possible box to this. So I'm going to take this fitness criteria and plug it in to there. Now, Galapagos can now change all of these criteria. And when it does, it'll reference in the change of difference in the volumes. And so it'll understand how this sort of process is working to build what we call a fitness landscape. And so what this is with these three criteria, there are a three-dimensional space that can be built from this, and it's applied to a four-dimensional space. Now this is difficult to visualize, so let's think of it just in terms of 2 degrees of freedom, this way and this way, which won't get you the smallest box, but it'll get you something that we can visualize more effectively. So if we say that all the permutations of degree 1 and all the permutations of degree 2 are mapped in an XY plane, whereas Z will tell you what this difference in volume is. So if you map those and you build that surface, you have a fitness landscape that represents this sort of function. So let's see if we can build that a little bit. There is a fitness landscape sort of component that will make this. What we need is some sort of bounding box. So we can make a rectangle. Let's say this goes from 0 to 90. So we'll use that as our X and Y directions. And then it needs all the values for that. So we have these two values. If we cross-reference these two values to get all the possible combinations of those, or actually not those two values, but a series of values. From 0 to 90. So if we get all the combinations of those values, you'll see that we have roughly 81,000 values. So let's plug those into our rotation criteria. You can see that these are all the rotations that are possible of that bounding box, which becomes a huge sort of data set to look at. Now, if we take these volumes, now I'm going to flatten these values so it comes in like that. And I want to tell it how many of these criteria we have, say in the X direction, which is that's what this is asking for, X direction. So it's going to be, if there's 90 points that we're plotting, there's actually going to be 91 sort of divisions of that. So I can plug that in, and then I'll say X plus 1. Let's turn some of these things off so you can see if we can visualize this a little better. Now our values are probably getting stretched way far because that volume is a pretty large number. So let's remap this terrain to something scaled down. So what you see is that this is, say, the x direction and the y direction of these two criteria, and it's mapping in terms of volume. So where you have high volumes, you have a high elevation, and low volumes, you have a low elevation. So looking at this, I can tell that this is probably our low point. So something in that range would probably give us the right sort of rotation. Now I don't know what these numbers are in the x or y direction that'll give me that, but I can use this evolutionary solver to determine that. So I'm going to get rid of our third dimension and just use these two. Our landscape will go away because we're not previewing that anymore. So let's see if we can find what that is. So if you double click on Galapagos, you can see that the solvers show up here, or the options show up here. The fitness, we want to minimize that volume. Everything else we can kind of leave as is. And then if you click on solvers, you can start this. Now it'll start rotating. You'll see that over here it's going through all the permutations of that. Now it's randomly selecting points, and it's trying to find ones that have low volumes, and then when it finds those, it'll recombine them to try to find other ones that are in the similar realm, slowly working its way to the most efficient bounding box. Now we're only using 2 of these, so it's not going to be the most efficient, but we can hopefully map that on that surface. So it's going to run through thousands of these iterations as fast as it can to sort of understand that landscape. It doesn't know what the function of this process is, so it's trying to figure out what that fitness landscape is so that it could determine where the lowest point is. So it gets to a point where it stops, it either finds one or it runs out of iterations. You can see that the lowest volume difference is this one. It's not exact, and you can see here that it's sort of only working in 2 directions, so it matches in these 2 ways, but we still have a lot of extra over here. So that sort of situates us in that lowest point for these 2 criteria. Now if I add a third criteria, it adds another dimension that's going to be very difficult to visualize, and also would be very difficult to see. There's 729,000 possible alternatives for this. So that might crash the computer if we do that, so I'm not going to do that. But in terms of the solver, I can plug this in to this Galapagos, and I can run it again, and I can see it starting to think. And it's slowly rotating. Oh, actually, I need to stop this. I never plugged in this as a genome. Okay, so if I return to that, it should be rotating these around, sort of understanding the fitness landscape of that, slowly resolving itself into something that's closer and closer and closer to the actual bounding box. Now this, depending on the problem, might take a couple minutes, it might take a couple days. It can take a really long time. Evolutionary solvers are not speedy sort of processes, but they're pretty flexible and they allow for a lot of calculations to happen that you wouldn't necessarily know about unless you use this system. So they can be helpful in some situations, but in other situations they should probably be avoided. So this is sort of testing that process. I can sort of see what these criteria are, allow it to sort of click through faster and faster so I don't have to visualize those, or I can see just the highest performing ones. Now if I allow this to keep running, it might eventually find something that's pretty close to it. Now the benefit of evolutionary solvers is you're constantly getting the highest or lowest value that you're looking for, though it might not be a close one. So I could stop this right now and get some value that's closer than I was before. If I allow it to run further and further, it should get a better and better solution every time. So now we've already cut down what was our 2,000 unit volume difference to something around 250. And if I allow that to continue, it should get lower and lower and lower the more iterations go through. So I allowed this to run for a couple minutes, and you can see I got close to 258. It's slightly off. Seen it get closer than that, but you can kind of see where it wants to go. I think actually one thing that I can do to help this is if I also allow it to go to -90. Now, shouldn't need this. But let's see if I give a full range of values. If it can get any closer. So it's already started to get a little closer. You can see it wasn't able to turn all the way around. So now that I have a little more leeway and this number wants to stay around negative something, so it wasn't able to do that before, I'm getting much closer. So I'll go ahead and stop it there. It's close enough for me. And you can see that I found a pretty good bounding box for this geometry. So you can use this for a lot of interesting scenarios. We'll maybe try a couple more in the next videos.